All right, are we ready?
Yeah.
Let's go. Okay, so we left off. We talked about we're gonna go back to the beginning. We talked about arrays, vectors, decks, linked lists, hash tables, and B trees and sets. Are there questions about those? All right, so then we can just go straight to graphs then. All right, so a graph is a structure in which we want to store an object or an entity. It can be any object or entity. We also want to store relationships between those entities. Now, that's kind of similar to, something like the object relational model, like like in a SQL database. And you could definitely like represent a graph in a SQL database somewhere. But a graph is a two-dimensional structure, at least where its edges are concerned, in the sense that you have just a list of objects somewhere, and any object can theoretically have a relationship to any other object. Now, the survey said there's not a whole lot of familiarity with graphs in this class. Has anyone taken like social media mining or the algorithms class or yeah, okay. Yeah. So we do have some familiarity then. Graphs can be represented in two ways, or they can be represented in more ways, but they're mainly represented in two ways. They can be backed by matrices or lists. And can someone tell me about those? Like, yes. So either an adjacency list or an adjacency matrix, and like, what's the difference?
So we made how they made we have another balance strategy. Like maybe the discount that probably nicely it's really nicely. And we all think kind of between the have been have a relationship,
Mhm.
but that means we really make it wrong.
Yeah. So the primary difference between an adjacency matrix and an adjacency list is that in an adjacency list, you only store information about the nodes that you have a connection to. And in an adjacency matrix, you store information about every single node pair, regardless of whether there's a relationship between the two or not. And so different structures will enable different algorithms to operate at different efficiencies, right? Because there are some graph algorithms that have actually been defined to in terms of matrix operations, like PageRank. And so PageRank has been defined in terms of matrix operations. So it's just a continuous matrix multiplication. And so for certain graphs, you can implement PageRank with matrix multiplication, which is really cool. However, there is a very big difference in what kinds of graphs you can represent with an adjacency list and what kinds of graphs you can represent in an adjacency matrix. Because large graphs with lots of different nodes, you can't represent that in an adjacency matrix very well, just because there are so many nodes. Like, for example, the identity work that I talked about in the first lecture that I've done for Count, um, it's a giant graph algorithm where we do community detection. So we try to group different vertices into, kind of subclusters and delineate them out. And that algorithm involves going through 6 billion different vertices, 6 billion vertices, and I think 17 billion edges. Now, 17 billion edges is a lot of edges, but that's way smaller than the number of possible edges that could exist in this graph. I mean, it's an undirected graph, but the possible edges that could exist are, what is it? Billion, trillion, quadrillion, quintillion, something like that. That many edges? 36 quintillion possible edges, but we only have 17 billion of them. But that's how many pieces of memory you would actually need to have in order to store it in an adjacency matrix, because that matrix would have to be so big. So in practice, we really only use the adjacency list, or at least something similar in the sense that we only store the individual pairs between the nodes that we know have a relationship. If there's no pair, then we don't store it and it's assumed that no relationship exists. Make sense to everybody? All right. Now you can have either directed graphs or not either, there are other kinds of graphs, but you can have both directed graphs and undirected graphs. And can someone tell me the difference between a directed and an undirected graph?
So I think that the right, yeah, it's kind of a school where you go. You can go either in the underwater graph and the next track. But for directed graph, you can go with the direction of the timeline.
Yes. So edges have a defined source and destination in a directed graph, and they don't necessarily in an undirected graph. So in a directed graph, and it's exactly as you said, the direction of the arrow between these two nodes matters. So, node A having connection to node B is not the same as node B having a connection to node A in a directed graph. In an undirected graph, the edges are bidirectional in the sense that the relationship of A to B is the same as the relationship from B to A. And there are some graphs which are directed, and there are some graphs which are inherently undirected. Can someone think of an example of a directed graph? Hmm? Yeah, that's a good example. Because when you're friends with somebody on Facebook, you're automatically friends with each other. That's a bidirectional relationship. So if, I'm friends with you, then you're friends with me. But in Instagram, it's totally different. I can follow you, but that doesn't necessarily mean that you follow me. So you have to keep track of those two pieces of information separately. That's a good example. Another example of a directed graph is Wikipedia. Wikipedia can be modeled as a directed graph. You have articles in Wikipedia and you have links to other articles. And so when you click on a link, you can go to another article, but that doesn't necessarily mean that you can find a link in that article that links back to the original. So Wikipedia is also a directed graph in that sense. And another good example of an undirected graph is this may not always be true, but flight routes is that if there exists a route that an airline is servicing between two cities, it's usually that they'll go from one city to another and they'll go from the other city back. So like, Boise has service to, cities like LA and Chicago and Minneapolis, Denver and Los Angeles. And those cities also have services to Boise. So that information is bidirectional as well. And so in addition to direction, edges can have, weights and other properties associated with them as well. And so, I don't know what kind of weight an Instagram following might have. Maybe it's a subscription. Can you subscribe to things? I don't use Instagram, so I don't know. Can you subscribe to things like for money? Okay. Okay. So yeah, so maybe the weight of those edges could be the price of your subscription or the type of plan you're using. Could be something like that. And for the routes between cities, it could be the cost of those routes, how much you would have to pay for a ticket, or how long the flight would take, things like that. So you can represent all sorts of very interesting relationships in a graph. You can represent practically anything as a graph. It's honestly really surprising. And since graphs are inherently recursive structures, you can also produce graphs from graphs. And in fact, that's what we do in our identity work at Count. So what we do in our identity work is, we process transactions, online e-commerce transactions, to analyze them for fraud. And so what we'll do is we have these transactions and we have information in those transactions like an email or a phone number. But these two kinds of entities are two totally separate things. You have transactions and they can be connected to each other in the graph indirectly because they might share an email. So maybe these transactions don't have anything else in common, but they do use the same email. And then on the other side of the equation, you have two pieces of information, like an email and a phone number, and they might appear in the same transaction together. And so they kind of share an indirect link that way. And so what we'll do for our graph analysis is we'll create something called a projection. And so this graph that uses both transactions and pieces of personal information, which we call PII, that's called the bipartite graph, in the sense that you have one group of nodes, and that group of nodes, let's say the transactions, they don't have any direct connection to other transactions in that graph. But they do have indirect connections because a transaction links to a piece of PII, and that piece of PII can link to any number of other transactions. And so what we do with the projection is we can say, all right, we take this original bipartite graph. We don't have direct connections between PII. We don't have direct connections between transactions, but we can create a projection where we only create a graph of transactions, and those transactions have an edge between them if they share a piece of PII. Or we can say that those two pieces of PII have an edge between them if they appear in the same transaction. And we can also assign weights to those edges. So for things like PII, if two pieces of PII appear in more than one transaction together, the weight of that edge could be the number of transactions they've appeared together. And so we can say that those pieces of PII are more strongly associated because they've appeared together more times or over a longer time span. So you can do all sorts of things with modeling these relationships. Though one other cool thing about graphs is that in addition to being able to model all sorts of things with them, there are also these very abstract general purpose algorithms that are applicable to almost anything. And so if you were to ask, like there's an algorithm in a graph called the connected components algorithm. It finds the connected components in a graph. Can someone tell me what a connected component in a graph is? Yeah. So a connected component is a subgraph where there's a path from every node in that subgraph to every other node in that subgraph. And so you can have multiple disparate subgraphs in your overall graph. And I can kind of show you what this looks like. So we have, let's see. You can use a tool called Network X that will model graphs for you. Are there any questions so far?
Does it have to be a complete graph? Does it have to be connected to every other component to accept that?
No, so that's a special kind of connected component called a click. So if you have a subgraph or a subset of the nodes where every node has a direct connection to every other node, that's called a click. And so that could be its own connected component, but it has a special name because in the general case, a connected component doesn't have to be that.
So a connected component is I have a node that's every other node I can get to.
Yes.
No matter how deep.
No matter how deep you go, just following the edges. And so we can create graphs with Network X and model them that way. So what do we want this graph to be? What do we want it to represent so we can play around with it? Okay, I'm going to do flight routes. So we can add a node for Seattle. Actually, we add a node for Seattle, for Boise, and then Chicago, Denver, New York, and so on. What? Did I get that wrong? Excuse me? It's singular? Ah, yeah. Add nodes from. That's what it is. Do that. There we go. Let's see. Are you seeing what I'm seeing? Okay, that was weird. Um, all right. So that gives us a view of the nodes. And so now what we can do is we can add connections between those cities. So we can say, G don't add edge. And we can add an edge between Boise and Seattle. And I'm going to choose the weight of every edge to be the cost of a ticket in dollars to travel there. So we're going to say it's $120 to travel between Boise and Seattle. And this graph is an undirected graph. So the cost to travel from Boise to Seattle is going to be treated as the same as the cost to travel from Seattle to Boise. So we can do that. And we can also add another route between Chicago and Denver. And that costs, let's say, $80. Wait, oh, add edge. All right. Now, we've added an edge between Boise and Seattle, and we've added an edge between Chicago and Denver. If I were to try and find the connected components, I just remember that a connected component is a set of nodes, and each set of nodes, within each set of nodes, you can reach every node and to every other node within those subsets. So if I were to run connected components on this graph, what would the components be? What would each set of nodes be? Hmm? Yeah. Yes. So there would be one connected component from Boise to Seattle, or including Boise and Seattle. That's one of them. And then another one of them would be Chicago and Denver. This is what we would expect to see. But then every other node in this list, it still exists, but it doesn't have any other routes yet. So New York is also in a connected component all by itself, all on its own. So let's see if we're right. We can ask Network X to perform connected components. What do we think? Are we right? Hmm? See what happens. There we go. So that automatically finds the connected components for us. And this is really useful because now it tells us if we start off, what connected components may tell us is I want to figure out where I can fly to, where it's just possible to fly to from one city to another. So if I started in Boise, what cities is it possible for me to fly to based on the fact that I start in Boise? It's just Seattle, right? But if I add an edge between Seattle and New York, or no, let's say that's $350. It's a little bit longer. And we do connected components again. What do we think is going to happen? Yeah. So New York is going to get added to the connected component that already has Boise and Seattle. So if we run it, then we can see that they all get added together. So this relationship is a transitive relationship. So if you remember from your math class, the transitive relationship means that if A has a relationship to B and B has that relationship to C, then A also has that same relationship to C. And so a connected component, it it is the transitive relationship between everything. That's what it is. And so using this, kind of abstractly connected components algorithm, if you wanted to ask this extremely practical question, okay, I started in Boise, where can I fly to from there? Using planes and using connecting flights, where can I go? You can use connected components to answer that question. Yeah.
Okay, so for trying to set stuff, it's not everything is going to be different. And you have to tell me anything about what I'm going to do, right?
No.
Most of the components are only going to tell you sets. So if, like, let's say from Boise, I could get to Denver, but we're going everything else first. It's just going to have Denver in the CG.
Yes. Yeah. And so there are other algorithms that will tell you, it's like, okay, what's the shortest path between two nodes in this graph? And in addition to what the shortest path is, maybe we want the cheapest path instead. So we could have, different weights on these edges mean different things. So we could say, all right, the edge between Boise and Seattle, the cost is 120 and the time is, let's say, 90 minutes. And so we can create these we can optimize these paths through the graph depending on what we want to optimize for. So if we want to optimize for cost, we can say, we can, tell whatever graph algorithm we're using, find me the lowest cost method of traveling between these two cities using flight, or find me the shortest method of traveling between these two cities using flight. And both of those will use, the shortest path algorithm between two nodes. And the shortest path algorithm between two nodes works on every graph. But you just have to decide what it means in that context. So in the context of the connected components, if we want to just see where it's possible to fly to, we ask this question about the connected components. But connected components can mean anything else in any other context. So a really good example is for the count identity work that we did, whenever we found the identities, so it does something similar to connected components in the sense that it finds sets of nodes to group together, but they're not connected components. Sometimes it adds cuts to the graph. So it doesn't do it strictly based on the edges. Sometimes it will stop early and create the community between nodes, even if there are edges to other nodes. So it's not a connected component. So it can still it creates these boundaries between sets of nodes in this giant graph. And so it still gives you a set of nodes, but between two different sets of nodes, there might be a path between them. So it makes that delineation by means other than connected components. So it finds out where the boundaries separating these communities are. And what we found was the base algorithm was creating boundaries that were too strict, in the sense that there were identities that were right next to each other in the graph that actually represented the same person. So it was being too aggressive with setting those boundaries. And so what I wanted to do was I wanted to create an algorithm where we could find, huh? Oh, let me, yeah. where we could find these identities that are connected to each other, look at them, and then see based on their characteristics, are these two the same person? Right? And then when we look at that, we can model the identities themselves and the relationship between these identities as a graph in and of itself. So let's see. We have the identity graph, which maybe this is an email, maybe this is a phone number, maybe this is a credit card, and this is another email, and this is another. Can we really see this? Let me use a darker. Yeah. Let's try this one. Oh, that's much better. Okay. Okay. This is an email, and this is a physical address of the house, and this is another credit card. And so there's connections between all of these, and let's say our algorithm, and there's a connection between this email and this phone menu. But let's say that this connection is kind of weak, and so we want to draw a boundary. So we say, okay, this is one identity. And we draw a boundary over here, and we say, this is another identity. These identities have a connection to each other because the PII in those identities also has a connection. So that's how we define, this relationship. And so we can look at these two individual identities, and we can say, do we think that these things are actually the same person? Maybe the connection on a network level is weak, but we have other information besides this connection that we can use to make that decision. And so the initial community detection algorithm only uses network information, but this other algorithm that identifies duplicates also uses information that's maybe inherent in the email or information that's inherent in the phone number, and things like that. And so then we can decide, okay, are these two identities the same thing? But then an identity can be connected to almost any other number of identities, right? There's no real restriction on it. And so let's say we have another identity here with a bunch of other PII, and those two have a connection to each other. And then we have another identity here, and it has its own PII, and that also has a connection. And so we have to say, okay, are these two the same? No. All right, so we're gonna keep this boundary that we set. Are these two the same? Yes. So we're gonna combine these two into one. And are these two the same? Yes. So we're gonna combine these two together. And so what I did with connecting components is I said, okay, so we can ignore the boundaries that we think are good. And we can take the pairs of identities that we think are the same, then using the fact that these two identities are the same as an edge, we find the connecting components of that, and every connecting component, we merge that entire component together into one identity. That is a real world application of connecting components that is being used in a count product right now.
So probably when we merge all the identities together, and let's say that we have like two different how we does it. How do we know that which will most visible people because?
So you're saying, this
Yes.
identity has an address?
Yeah.
Okay.
This one have address too.
Yeah.
Yes, and so we will keep two address and we will.
You keep everything. You keep everything. So this has an address, and this has an address, and these two things might not be the same address. Yeah. And so not only do we have current information about this identity, we also have historical information. So maybe this information is older than this information. So maybe you moved somewhere and you got a new credit card, and it's actually This is a phone number. And so maybe you move somewhere and you got a new address, you have a new credit card, and maybe you also decided to use a different email, but you use the same phone number. And so because you use the same phone number, you use the same phone number and this new credit card in a transaction together. So now there's a link. So now that gives us the information we need to know there's a link on a comparison. Because we have 700 million identities in our data set. There is no way we can look at every possible pair of identities and make our decision that way. So we have to narrow it down somehow. And the way we narrow it down is if there's an initial connection in the PII in these identities, then we do the comparison. And that's our criteria for running fewer comparisons because there are just too many otherwise.
Because you compare all identities with some edge.
With some edge in between?
And edge.
Yes.
Okay, and our edges are these identities.
Yes.
With a transaction that shares some reserve value.
Yes.
So when you first decided to set up this network, we first have the transactions lines and PII taxes.
That is something I have brought up to the data scientists that they have told me is not worth exploring. I disagree. And that is something that I will continuously bring up until Maddie lets me do it.
The Python version of the is it's only in lists or amendments or how do you decide like certain has limitations.
I mean, yes, my assumption is that it's an adjacency list. And so honestly, an adjacency list might just be the default because out of the two, it's the more memory efficient option. And because there's a quadratic relationship between the number of nodes in the graph and the amount of space it would take to store the adjacency matrix, it's usually just better to assume it's an adjacency list. Unless you have a reason to use one. So that's what happens. So does this use case make sense? Are there any questions about that? The connected components idea make sense?
On those edges?
No. So okay, there are weights on these edges, but we don't actually use them.
So have you found that if you have more connections, it's more like linear genius? How long is this? How long is how long is your identity?
Okay. So this is the entire process to build the identities and to calculate statistics on them. It's a single giant Spark program. And there are a bunch of different stages to the Spark program. It has to clean the transaction data first. It has to build the graph because it doesn't start out as a graph. So we have to build it. And then it does, some other munging and filtering out some bad nodes in the graph. We know that some nodes are actually duplicates of each other. Maybe there's a typo or something, or maybe the zip code changes because USGS likes to do that. The address is actually the same, but the zip code changes because government reasons. And then after that, we, run our initial boundary drawing algorithm to create these subsets. And then once we have the subsets, then we can look at connections between the subsets and then do the merger. It's a long process. I've spent the last 3 years at Cowan writing and maintaining this.
So when you update this, are you adding more to this graph? You're not rebuilding the graph.
No, we're rebuilding the graph. So whenever we do that algorithm on 6 billion nodes, we redo it in full every time. And that takes 12 hours.
So the reason why you do everything is that what?
So the reason is that the algorithm we use to draw like these original boundaries, it's a global algorithm. And so it requires access to the entire graph in order to do its job. And so because it has to process the entire graph in parallel, we just spin it up and we analyze everything, and then it acts as kind of a snapshot. So we rerun this algorithm every month and we redraw these boundaries every month. And then we serve that new data to customers every month. Yes. So we have new transaction data coming in every month. We got like 100 million new transactions per month. And that will change how these boundaries are drawn from month to month. We use the
Constantly adding in.
we use the entire historical data.
And is there a limit? I know that at this point, yeah, we need to bring that processing time.
No, we'll just give it more hardware. I mean, that has actually happened several times, is uh because counts traffic has exploded a lot in recent years, and so we get way more transactions per year now than we did like 5 years ago. And so 5 years ago we might have gotten 500 million transactions in a year. Now we're getting like 1.5 billion transactions every year. And so this process has broken several times because it has too many transactions in it. And so I have to beef up the cluster and give it more hardware to work with. And so, we used to be working with maybe 4 terabytes of memory. It's a lot of memory. And, like 800 cores. And I've had to beef it up to like over 1,000 cores with 6 terabytes of memory. And we can just keep increasing it because Spark scales that way. That's why we study distributed processing systems, because there are cases that they are not good for, and we'll talk about those later in the semester, because I have had to write big data applications whose analysis is too complex for a distributed system. So I had to figure out how to make it work on one machine. And so we'll talk about those cases later. But the reason we're studying Spark is that if you have Spark and you have access to it and you know how to use it, it's an extremely powerful tool.
So I get the help there to run a little bit faster and not asking anything to do
I do kind of make a guess. I usually don't increase it by that much every time. So when I beef up the cluster, I'll usually maybe like a 50% increase in hardware, because I don't want to have to keep increasing it every time. So it's kind of like that over allocation strategy for data structures we talked about last time. You just give it some extra hardware to work with and it'll be fine for a while until it breaks again. And then we have to increase it again. Yeah.
Anyway, customer side by the transaction, sa kabi of line, the function component of the that's
Like Google Flights. Yeah, so like you can book flights through Google, and almost every booking app will do this. Is Well, not necessarily for connected components, but it'll use an optimization algorithm. Like these optimization algorithms probably exist in here somewhere. Here, I'll just ask ChatGPT. Network X shortest path. Oh, there we go. It's called shortest path. Wow. Okay. So we can look at um, shortest path. What's the shortest path? Let's say between Boise, the graph source is Boise, and the target, we want to go to New York. What's the shortest path? What just happened? Wait. Oh, I have to spell it out. Okay. So now it's giving us a path. We're going to first go to Boise, and then we're going to go to Seattle, and then we're going to go to New York. But now what we can do is you can also do it for a weighted graph. So we can say, let's redefine all of these. So you can say the cost is 80 and the time, how long does it take? I'm going to guess it's about 2 hours, probably less than that. Say cost. Time, that would probably be about 6 hours. And we can optimize for different things. So in order to make this experiment meaningful, we have to add multiple options. So let's say there's also a direct flight between Boise and Seattle that cuts the time off a little bit. Let's say it's only 5 hours, but let's also say that the cost is like $500. So that's more expensive. So the connected components, we added this new direct edge between Boise and New York, but the connected components stay the same because regardless of whether the edge is there, you can still reach New York. But the shortest path is going to change. So network X by default is going to treat every edge like it's worth the same amount. So this shortest path is going to change where it's just going to directly go from Boise to New York because it doesn't know what you want to optimize for. But we can specify a weight. We can say, I want to actually optimize this by cost. So if I were to optimize by cost, what would I do? I'd go through Seattle. But if I wanted to optimize it for time, then I'd go direct. And I think this is really cool because the graph is a generic data structure. Network X, this library, has no idea we're using this to track flights. But it's still useful. All the functionality that we need is already there. So these general ideas are very, very widely applicable. Questions? All right. Okay. Questions on network hacks or anything like that? All right, cool. Okay. So we just discussed like, 5 or so different data structures for these kinds of things. So if we were to look at the first five, you know, arrays, vectors, or slash vectors, because they're really the same thing. They're called vectors in some languages. So like in Rust and C++, a dynamic array is called a vector. You can use a deck or a linked list or a hash table or a B tree. So for a graph, so like maybe think about it for a couple minutes. You can discuss it with the people next to you. For a graph, if you had to represent it as an adjacency list, how would you use these data structures, these first five, to do that? So we'll take five and think about it. And you guys can talk to each other too, share ideas. Yeah. So what data structures would you use, out of these? Or you can use some other ones that we didn't discuss in class. What would you use if you needed to represent a graph as an adjacency list? All right. What do we think? Huh?
I think they choose this method.
B3 is more flexible? I mean, yeah, we can use any kind of map that we want. So, you could use a B tree for that. Let's see. So we imported the B tree. Um, which one would we use? Would we use a B tree set or a map? Map? Okay. You can use an order dictionary. It's sorted. Excuse me. Okay. So we've defined which data structure we might want to use. Um, what would the keys be and what would the values be? Yeah, so the key would be the node. Um, so we could say graph of Boise, or we probably have to say set value or something. Forget what the actual method syntax is. Set item. Okay. Yeah, it's set item. Okay. So what would the value be? So Boise is a node in this graph. Huh? Yeah, so we could represent it as a list of neighbors. So we could say the neighbors of Boise are Seattle and New York. Well, they also have attributes associated with those edges, right? They have a cost and a time. I don't remember what those are. 120 and 90 and 500. Okay. Okay. So let's say we use the structure like this. Um, so we have information on every node that Boise is connected to. But what if I wanted to ask, all right, so we know all the things that Boise is connected to. What if we specifically wanted to find the cost to travel from Boise to New York? What would we have to do that in this structure? Yeah. So yes. So what we could do instead is what we could do instead is we could say the value is also a map. So the key is exactly the same. It's the node, but the value is a map. And the map is a map between the destination node and the rest of the attributes for that node. So we could say that these would be tuples. These are specified as tuples in the constructor. So we can do something like that. So it would kind of be a map of maps. And that's what we could do. Because the alternative is, okay, we grab the list for Boise and we have all of the, do you have a question? Okay. And we have all the nodes for Boise. But then once we have all the nodes for Boise, we have to search through all of them until we find New York. And there could be thousands of these things. And so maybe a better way to do it would be to store the adjacency list for every node in itself as a map. So this is like a map of maps. And so now we can efficiently access both the source node, because the top level structure is the map, and we can access the destination node, which is New York. And that gives us the information that we want. And this is only logarithmic time instead of linear time, since we're searching through a B tree instead of searching through a list. Yeah.
Okay, we already have it in the four, we still have these. We did learn a piece. Friends who did that story. How would you like that if you didn't? When we just go to the four.
Oh, so over here? How do we have found it? Okay. So we would do something like um we would say destinations is equal to graph of OC. And then we would look through every destination, and then you would say if actually let's see. Yes. Or actually, yeah. Yes, we have to iterate through to find the data. So that's a two-bit. Let's just make this a function, actually. Get cost. Let's just see the graph. We have the estimation. Then we can return. Which one did I make the cost? Was it this one or this one? It was the first one. Okay. Okay. And so then if we don't find the destination, then we can do return null. So then we can look through. Then okay. So this, what just happened?
Yes, I got this.
Oh, yes. There we go. Okay, so that gives us the cost. But this also requires us to look through every other node in that list. So if we can see the traversal if we just print it out. So we can see it going from Seattle to New York. And so it'll go through the entire thing. But if we just do if we do this as a nested graph, then so looking through that entire list is a linear time operation. And so, as we continue to scale, if we were to, try and do this in a real-time system, that, might get high latency. And so ideally we want the lowest latency possible. So you could definitely use like a nested set of maps for this. What would work equally well in this case is you could just use a normal Python dictionary. Yeah, you could use a hash table. So you can use any kind of efficient map. So you can use a B tree for a map, and you can also use a hash table for a map. So which one you use depends on what you want. Usually what you would do is a hash table. And that's because hash tables are, well, frankly, more common in fast implementations. Like the language we use at Count to implement all of our software, which is Golang. Golang has a built-in hash map hash table type. It does not have a built-in B tree type. So you have to use external libraries for B trees in Go. You don't have to do that for hash tables. Some of the advantages that B trees have over hash tables are the fact that B trees do not give you an amortized time. So let's like we discussed last time, is that hash tables are usually backed by an array. And if you're continuously adding stuff to the hash table and the hash table fills up, then you have to reallocate it, copy everything over so you can keep adding more things. With a B tree, you don't have to do that. The adding something to a B tree is always going to be logarithmic time every time. So that's one advantage. But um, retrieving an element from a hash table is constant time as opposed to logarithmic time with a B tree. And so what I find really interesting is that the Rust standard library has both a B tree map and a hash map as part of its standard collections library. And they have basically said straight up is most of the time you want to use a hash map. But if you need your keys sorted, or if you can't tolerate amortization for any reason, or whichever, you can use a B tree map. A hash map is usually faster.
This is only set out, it's only organized to search for the from Boise designs, right? So you created this feature to the, and then you said, now I really imagine whether you populate wants to go from me to sit.
So you'd have to copy this over. You'd have to basically have two copies of the data, one for the source and one for the destination. And in fact, that's what we have to do when we're writing graph algorithms in Spark, because we'll cover this in more detail in the future, is that you cannot access data easily that is on another machine. You can only access data that is on the same machine as the code that you're running quickly. So what we do a lot of the time is we will duplicate the data so that is indexed differently. So even though the information is exactly the same when you go from Boise to New York or New York to Boise, that information still needs to be duplicated because on one hand, you might be calculating it with respect to Boise, and on the other hand, you might be calculating it with respect to New York. And so if all the data from New York is in one place and all the data from Boise is in one place, that makes things really nice. But you can also do the alternative, and you could say, instead of storing these as nested bunch of B trees or a nested bunch of maps, you could just store the pairs. So you could say that graph and then graph of Boise, New York. Equals 500. So what I said, yeah, okay. So you could also represent it this way. So now you only need to represent it one way if you standardize it. So if you're like, okay, we have this pair because as far as Python is concerned, right, Boise, New York is going to be different from New York, Boise. But you could say, all right, if we're searching for a pair of cities, we'll always sort them alphabetically. So Boise is always going to go first because it starts with a B. So you could say something like that. So now the amount of space that you would take up with this hash table is half, probably even less than that, but half of what you would have to do if you were duplicating the data twice. But what's the flaw with this structure? What can you not do with this structure that you can do with this? Well, you can add lots of layers. Why are those layers useful? So what does it allow us to do quickly over here that you can't do, or not over here, sorry, over here. So what can you do quickly over here you can't do quickly over here?
if I have, let's say, I want to get to Chicago. And the only way is to get to Chicago is to be in New York. What are you storing that bit? Are you going, are you storing at Boise, New York, Chicago too? Or are you just storing at Boise, Chicago to cut that bit?
That's the thing, is you can only query this if you know in advance that this pair exists. Right? So it would be extremely difficult, using a structure like this to go through it and see, okay, what are all the flights to and from Boise? What are all the flights to and from Chicago? Because all of those things are spread across the entire data structure. There's no reason to believe that they're in the same place or that they're next to each other or anything like that. So what this does is, even though it duplicates the data, it introduces some locality to it, right? So everything that's going from Boise is in this submap, is in this data structure. So now we don't have to look at every other key in the top level map. We only look at the Boise key, and then we can look at every key in that much smaller map. So it allows us to partition that data. And this kind of data partitioning is a very common technique for making database queries at a large scale actually possible.
But why did we do this instead of using actually a graph?
Well, this is how a graph data structure would be represented, like under the hood. This is probably what Network X does in order to represent it as a graph. Yeah. Or either a B tree or a hash map or a map of some kind that has an efficient key lookup. So the key lookup in this B tree map is logarithmic time. The key lookup in a hash map is constant.
And how do you know if I'm trying to process a combination of the basic ways? You not have to do it. You need reference of you. You have to do it. You call, you follow. So
I don't see the distinction.
So let's say this is something I really like as in using, well, I'm using stuff. I want to know Boise to what I'm using. Okay. And if I'm like putting in a database and I'm getting that page program, I'll do the database.
Mm-hmm.
But how do I know? I'm not clearing my JIT, I'm just following this and asking for this too.
I mean, sure, but there are databases that are basically just a giant distributed hash table. That's what Dynamo is.
So you keep a database of the keys. You know what you meant?
Well, yeah, so I'm making a lot of analogies between basic data structures you would use in code and entire databases, because a lot of the time they have a lot of these same structures in common, right? Like a Postgres database, a SQL Postgres database, when it needs to index on a column, it uses a B tree. It uses the same thing that you'd be using in this code here. It's accessed differently because one is on disk and one is in memory, and so the exact um, dealings with it are a little bit different, but the structure is the same and the content and the concept is the same. And so I'm going to make a lot of comparisons between, like, oh, you have this access pattern in your data structure and you have this access pattern in your database. You can use a lot of that same knowledge because a database, a lot of the time, is just a data structure. Like the Dynamo is a distributed hash table. And more specifically, it's a distributed hash table where all the keys in this broad table, this hash table is spread over many, many different machines. And so it uses a hash function not only to decide which place on each machine it goes to, but it also uses a hash function to decide which machine it asks for each particular key. So Dynamo is just a distributed hash table where the keys can be, strings or numbers or, binary vectors or whatever. And the values are B trees. Because within a partition key in Dynamo, the values are sorted. So I'm willing to bet under the hood that's a huge reduce. So AWS services Dynamo database can really just be thought of as a giant distributed hash table. And you use a lot of the same considerations when picking a database architecture that you would do when just picking a data structure when you're coding. A lot of it is the same. A lot of it is the same logic, where it's like, okay, I want this access to either be logarithmic or constant time. Which data structure gives that to me? Is there a database that is basically that data structure? You can make a lot of direct comparisons. Any questions on that? So this is also what happens when we cluster tables in Snowflake. So when we cluster tables in Snowflake, we'll say, oh, this table in Snowflake is clustered by the source city, wherever we're flying from. Well, the source city is Boise, so that means in this giant database, everything that's flying out of Boise is actually located in the same place. So we only have to access one thing in order to get all the information about Boise, if that's what we want. So it can be much more efficient because our data is organized differently. So we don't have to scan through the entire thing to look for Boise, just one little piece of it. Maybe. It might be. But Snowflake is fundamentally different in the sense that when the data is partitioned in Snowflake, if you make a change to a partition, the entire partition is written at once. So I'm willing to bet that Snowflake might just be a stored array. It might just be an array because when you insert something into the partition, it just rewrites the entire partition because it kind of assumes you're doing everything in batch. That's one of the core differences between a data warehouse and a database. Is that a database is optimized for low latency and a data warehouse is optimized for high throughput. We are over time. Are there any questions? Oh, awfully quiet today. All right, if there are no more questions, we're done. And office hours are now, if anybody has questions.